Having looked at conformational changes, let's return to the issue of stereoisomers. If these two molecules were frozen in the conformation that's shown here, they're stereoisomers of one another. They're diastereomers. However, what we now know is that the barrier to interconversion between these two is rather small, meaning that they'll interconvert very rapidly. Certainly at room temperature, they'll be happening millions or billions of times per second. So although these are two stereoisomers, in practice, the interconversion between these different stereoisomer forms will average these molecules out, and we wouldn't be able to physically separate these two. Compare that to the case that's shown for cis and trans butene. These are also diastereomers of one another. However, unlike the case that I just showed you, the interconversion of these two by some potential rotation about the carbon-carbon double bond does not take place at all. Cross that off, it's not possible at any reasonable temperature to interconvert between these two diastereomers. So we could physically separate cis-butene from trans-2-butene. Another aspect having to do with stereoisomerism and timescale is the process that's known as configuration inversion. The process of configuration inversion is very common to the nitrogen of the amine functional group, as we'll see here. That nitrogen has 3 single bond domains and a lone pair domain, and if each of these 3 substituents are different, the lone pair represents a 4th type of group that's tetrahedrally arranged around nitrogen. That would create a stereocenter, but that configuration doesn't last very long because the process of configuration inversion, or pyramidal interconversion as it's sometimes called, takes that configuration through a planar form like you can see here and puts the lone pair on the opposite side of that reference plane so that the configuration at nitrogen has completely inverted. The barrier to this interconversion is very small. The process takes place on the order of 1 billion times per second. In the example shown here, this trans diastereomer converts to this cis diastereomer by the process of pyramidal inversion at nitrogen. That causes the methyl group in its down position to go up to the up position. Since this takes place at 1 billion times per second, it would never be possible to put these two molecules into separate bottles. Now we're in a position to summarize for the general case in which a structure A transforms into a structure B by a process that involves a barrier. The rate for the forward direction, K sub F, the process of A transforming to B, is going to depend on that energy in which A travels over the barrier to get to B. K sub B, the rate constant in the backward direction, is going to depend on the barrier height traveling from B over the barrier to get to A. The ratio of A to B is going to depend on the difference in free energy between those two minima, and that's going to be related to the equilibrium constant, capital K, which is the ratio of those two rate constants. And so you can see from this potential energy curve that we know an awful lot about the process of how A and B interconvert.